Welcome back to the blockchain technology and applications. We were talking about dApps or Ethereum based applications that are interacted with by users through web interface, and the underlying technology of smart contracts and blockchain can be hidden. Now, as I said that we'll give you some indicators as to where to go and learn more about it towards the end of this lecture, but before that I want to point out a certain few other things about Ethereum, which Ethereum Foundation, so these are from the documents of white paper of Ethereum Foundation, which basically explains their choice of the design of Ethereum, which is quite different from Bitcoin, although both are cryptocurrency blockchains and both are permissionless blockchain and both are pseudo-anonymous and both have the notion of transactions and mining and hash puzzles and everything, but still they have very different design principles on which the entire design and architecture of Ethereum was done. And this is done because the Vitalik Buterin, who is the originator of Ethereum, was using Bitcoin blockchain for a while, and then he realized that there are certain things that are not very easy with Bitcoin, and there are certain design principles that he didn't like of Bitcoin, and therefore he is explaining here, and I think you should know that because one of the goal of this course is to actually give you more conceptual handle on the blockchain technology than nitty-gritty programming practices of blockchain. So you should be able to explain to somebody who is asking what's the difference between Ethereum and Bitcoin. Of course, you can talk about smart contracts, you can talk about Solidity, which is Turing complete language, but there are certain other things, more higher level principles that are at play here. So Ethereum has this notion of what they call sandwich complexity model. So sandwich basically means that it has three layers, right? So top layer and bottom layer are bread, and then middle layer has something like a meat or some vegetables or something. So here also the idea is that all the complexity is in the top layer and the bottom layer, and then the middle layer is kept as simple as possible. So complexity is handled at the high level with the language, Solidity language and the language compiler, argument serialization and deserialization scripts. That is when you have complex data structures that are part of your arguments in a function call in a smart contract, how they are serialized, because they have to be traversing the network, right? So therefore then there is need for serialization, but the user doesn't have to do these things themselves. There are already scripts which do the serialization, deserialization automatically, so user will use it like a normal function call. Storage data structure models, and then the level DB storage interface at the bottom layer, that's where the information is stored, and the wire protocol, that is the peer-to-peer protocol that is used for interacting between the nodes in the blockchain. So that's the idea of sandwich complexity model. So this is not something that the Bitcoin used, right? So Bitcoin has kind of a monolithic complexity, and therefore the user, like who puts transactions, have to either know a lot more the working of the Bitcoin mechanism in order to write complex scripts. Here the programming model is very much like a regular program, like when you write regular programs, you don't think of like the computer architecture, the registers and program stack and all that stuff when you write your program. Similarly in Solidity, when you write smart contracts, you don't think of the underlying architecture, microarchitecture of the EVM and all that issues. So that complexity is kind of hidden from you. So there is another idea of freedom or net neutrality. So if you have noticed in Bitcoin, it's very biased towards only Bitcoin transactions. So we talked about how you can use Bitcoin to actually store some data permanently or timestamp some data permanently, but usually those are not favored. So the way the Bitcoin has been designed is kind of singularly meant for the Bitcoin transactions. So what they decided is that we should not restrict the users, so that they have that the system or the platform preferentially disfavors a particular type of transactions or particular type of applications. So it's kind of net neutrality inspired idea that any kind of application, it could be cryptocurrency application, it could be e-commerce application, it could be just data storage like land record where you are trying to guarantee the integrity of the data, or it could be a grid management system. All that stuff can be actually managed in this with equal difficulty or equal simplicity. So that's the freedom principle. Generalizing principle is that all the protocol features and opcodes in Ethereum are actually low level concepts. So they don't create high level opcodes which do a very high level, that an opcode that basically it says do something very complex. So everything is a very low level simple opcodes. Semantics are very simple low level ideas. So one can actually use them in arbitrary ways, so create very complex functionality. So more, it's like like if you want to do something very complex, assembly level programming might be more flexible for you than, let's say, you are using some high level programming language like a functional language, and then you have to do a lot of trickery to make it do something complex and not something that is not meant for by the language designers. Here they didn't do that choice, and it's very generalizable. And therefore, as a principle, as a corollary to this principle of generalization, they have very few or almost no high level features. And they expect that if you want to create high level features, you can create protocols on top of the Ethereum protocol. So you can make ether backed subcurrency, you can define your own tokens, and like this is how the ECOs are done, and you can also mimic other kinds of coins and etc. using subcontracts. So that flexibility is there. So it's four principles, that design principles, is that the complexity is kept out of the user's purview. The freedom in the sense that it does not disfavor a particular type of transaction or favor a particular type of application on top of Ethereum. It's generalizable, and generalizability is probably the core to this freedom, and because it basically uses all opcode semantics are very low level concept based and not high level, and then therefore as a corollary it's low in high level features. So remember this very high level design principles that drove the creation of Ethereum and the design and architecture of Ethereum. So another difference that is interesting in case of difference between Bitcoin blockchain and Ethereum is in Bitcoin there is no concept of a real account. Everything is kept track of by unspent transactions, right? So whenever you give some money to another person, you have your digital signature on it, and then whenever you want to use that money, you have to use that as an input transaction, and then you create output transactions. So these UTXOs are the ones which are not yet used. So these UTXOs are kept track of. So that's kind of the state of the current state of the blockchain. So in Ethereum, however, we don't keep track of UTXOs. We have the notion of accounts. So every account, the accounts are two types. One is called EOAs, or external user accounts, and another is the smart contract accounts, right? So externally owned accounts and smart contract accounts. So these accounts have their addresses, they have ether balances. The balance could be 0, or the balance could be positive. but they have balances. So when you send money to somebody, let's say a real person with an externally owned account, then that balance will go up. If the person spends money from its balance, then the balance will go down. Similarly, the subcontract accounts also can keep Ether as balance and can send Ether to externally owned accounts or to other smart contracts for getting things done. So therefore, there are the notion of accounts and not UTXOs. In Ethereum, we saw that the transactions are kept as Merkle trees. In here, we see a little different concept. They use something called Merkle-Patricia trees, and we'll show you what this means. They have a different serialization format called recursive length prefix, and they have a compression algorithm. They use tries, which is a particular data structure on which the Patricia trees are based, and they have this notion of uncle incentivization, which basically means that whenever, so you have parents in case of Bitcoin blockchain, but there is no notion of uncle, because uncle is actually a branch that has been abandoned after the race condition that happens when multiple branches starts coming up, but eventually everybody starts building on top of the longest branch. So the other blocks that would be called uncle or grand uncle, they have no meaning, but here we have the incentivization for uncles, because then if two of you are making the next block, eventually one of you will become uncle, and then there would be some Ether that you will get for becoming uncle. So difficulty update algorithm that Bitcoin also has, but it's a different algorithm than Bitcoin. Bitcoin also changes the difficulty of the hash puzzle. This one also does that. And the notion of gas is completely not there in Bitcoin. Bitcoin has notion of transaction fees. Here we pay gas, and because we pay gas, we always have to pay fees. And then the Ethereum has this notion of EVM, which runs bytecode and which runs Turing complete bytecode, which of course is one of the major differences. So something to be said about this notion of accounts versus UTXOs. So Bitcoin stores users' balances in a structure based on unspent transaction outputs, or UTXOs. So the state of the system is a set of unspent outputs. So whenever you try to make a transaction, the input transaction should come from the UTXOs, right? Because then you know that there is no double spending attempt. So each coin has a particular owner and as we know that in Bitcoin, when you create a coin, when you either mine a coin, you become the owner, and that mining transaction is associated with your ownership, right? So when you want to spend that coin, you have to use that transaction in which you mine the coin as an input transaction, and then you have to, if you are giving the money to somebody, there will be output transactions, and you have to give the balance to also a different address, as we know that, because otherwise there will be replay attacks. So each coin therefore has an owner and a value, and a transaction spends one or more coins and creates one or more new coins in Bitcoin. And the idea is that every referenced input must be valid and not yet spent, so it should be from the UTXO, and the transaction must have a signature matching the owner for every input, and total value of input must be equal or exceed the total value of outputs. If the inputs exceed the total value of outputs, the difference between input and output total will be lost forever. The user's balance is a total value of the set of coins for which user has a private key capable of producing valid signature. So the balance is based on the UTXOs for which it has a valid private key. So that's the Bitcoin way. In Ethereum, the state stores a list of accounts, and at any point the current state has a list of accounts which are active and they have balance. So this data that is associated with the account is balance, and the code if it is a smart contract, and internal storage, right. So, various kinds of other information, the program state basically, because when you execute the program, you may change some state variables of the program. So, there will be those as well. Now, a transaction is valid if the sending account has enough balance to pay for it. So, what it will check is that for the account, it will check whether the balance is enough. It does not care whether that money came through which transaction. Say, so in case of Bitcoin, you identify exactly which transaction gave you that money, that becomes your input, and when you create an output transaction giving money to somebody else, then you are creating a new coin that you are giving to somebody else, and that somebody else then will have that unspent transaction until it spends it. Now, in this case, I might have multiple transactions, let us say one for 5 ether, one for 2 ether, one for 1 ether, then I will have an 8 ether balance, and this money becomes, these coins are fungible in the sense that they are replaceable with each other. I do not know which of these 8 coins came from the first transaction, which came from the second transaction, which came from the third transaction. The only thing that happens is that the sending account is debited and the receiving account is credited with the value. If the receiving account has a code, then it might do something else after it receives the ether, depending on what function was called to send the ether, and it may run the code, and there may be some state change also. For example, it might say that some flag may become true to false or false to true, or it might actually have some other information that changes that can happen, and even there may be a chain of transactions that may be created, because once this smart contract gets your ether, it might actually create other transactions to other contracts, send some part of the money to another account. All kinds of chain series of transaction may also ensue when you do that. So, benefit of UTXO is that it gives you a higher degree of privacy. So, because remember, in UTXO, every time let us say you have 25 Bitcoin and you are giving somebody 5 Bitcoin, but you give the 20 Bitcoins to a new address, and then when you want to spend that 20 Bitcoin, then you have to use that transaction with that new address's private key to unlock the money, the 20 coins, and let us say you give another 5 to somebody else, and then a 15 you give to a new address. So, addresses proliferate, and therefore, when somebody collects all the data from the past transactions blocks and try to figure out who is who and all that stuff, it becomes more difficult, because same guy will have many addresses. Whereas, if you have an account has a given address. So, therefore, and then you make a transaction you start with 25 ether, you give 5 to somebody, then you give another 5 to somebody. So, all those things will be easily tied to you. However, obviously, the account address is actually a public key in some hashed form. Therefore, that does not mean that you will be completely de-anonymized, but in Bitcoin it is even harder to put together all these transactions to attribute all these activities to you. And also, UTXs are more compatible with certain kind of scalability, and the owner of the coin maintains the Markle proof of the ownership, which basically means that it has the signature, it has the ability to do the signature, and it also has the transaction history, the hash of the root of the transaction history, which is called the Markle proof of ownership. And if the owner decides to forget that data, then only the owner is harmed. In case of an account, it's if you forget, then anybody who is supposed to get some activities, or everybody who has the ability to make transactions on that smart contract in which the ether balance is there, then they cannot, none of them can use the ether if that is forgotten. However, for accounts there is a lot of space saving. So, if an account, if suppose your wallet has 5 UTXOs associated with it. I mean, you only know because you have your wallet has all the corresponding private keys. So, you know the other guys may not know that all these UTXOs belong to you, because they have different public key associated with them, but you as an account owner would know that I have these 5 UTXOs because I have these 5 keys and they are unspent. So, however, to keep that information on the blockchain, you need about 300 bytes, 20 for an address, 32 for the transaction ID, and 8 for the value. So, these are bytes, and that times 5 for each of the UTXO. You need 60. So, 60 times 5, 300. Whereas in case of an account, you don't have to make it 5 times, right, because it's a single account. So, you need to know the address, you need to know the value, and you don't need to remember the transaction ID that brought that value in, and then you need 2 bytes for a nonce. Now, why is nonce there? Because the problem with the UTXOs are used because we want to stop replay attacks, right. So, we actually for every transaction we create new addresses for the balance, and therefore replay attacks cannot work. But in case of accounts, you have to use some kind of a way to distinguish every transaction. So, there is a notion of a nonce. Nonce is an once only number. So, it may be initially a random number. So, this actually is incremented and therefore you cannot replay it. So, transactions can also be smaller. So, 100 bytes for Ethereum, where 200 to 250 bytes in Bitcoin. So, and because every transaction need to make only one reference and one signature, whereas in case of Bitcoin, every transaction requires all the, let's say you want to spend 25 Bitcoins, one single UTXO which is given you 25, let's say you have 5 of them. So, 5 UTXOs will be your input, and each of them will have their own transaction ID and address and the amount and digital signature. So, it will require a lot more information per transaction, whereas in this case in Ethereum you only have to save the account address, the nonce, and therefore you will need less amount of bits to formulate the transaction. So, the benefits of accounts is greater fungibility, which we already talked about. That is, all the different sources are all put together. So, you don't have to remember that this came from this and this came from that. So, you cannot blacklist or red list a coin. You cannot say that this coin came through wrong type of sender, and so this UTXO now get banned. You cannot do anything like that, because all these things are fungible. Unless you want to ban the entire account, you cannot really do anything. So, coins are not distinguishable which transaction they came from. Of course, accounts are much simpler to code and understand, because you know the notion of accounts from your banking and other kinds of activities. And the light clients at any point can access all data related to an account by scanning down the state tree in a specific direction. And the replay attacks are prevented through the use of nonce. So, we already talked about that each transaction is associated with a nonce. So, that basically takes us to the end of the discussion on accounts. So, when we come back, we will talk about the some of the data structures used in Ethereum, as well as we will talk about the give you some pointers as to how you can start making yourself more familiar with creating smart contracts and Solidity language and so on.